Okay, so it's 10 o'clock and it's the last morning of the EAP 2021 conference on machine learning, and our first talk from the morning is Ingo Waldmann, who's going to give us a review on machine learning for exoplanets. So Ingo, please go ahead.
Thanks very much. Thank you for the invitation. I'm really sorry that I can make it in person. Yes, given that it's been a conference dinner yesterday, this is a nice way to guide you through your hangover. So, given that it's online, I can't see you. So you just close your eyes and just let it wash over you. It'll all be well. So exoplanets is, when I was asked to give this talk, I thought that's going to be easy enough. Turns out it's not, because exoplanets is by definition almost a very, very fractured field. There are many, many subfields with their own communities, their own conferences, and their own approaches, especially also to machine learning, because there are very different aspects that need to be solved. So it's a bit of a whistle-stop tour across this landscape. And I won't be able to cover everything, but I'll do my best to give you an idea of what's going on in exoplanets with respect to machine learning. So to give you just a quick overview of where we are at with exoplanets at the moment. So what you have to remember, we're still a very young field. We're 31 years younger than cosmology, modern cosmology. So the first exoplanet discovery was in the early 90s, and then 51 Pegasi b really kicked everything off in 1995. So we got a Nobel Prize for that recently. And you can see this is a cumulative distribution of exoplanets discovered since, dragged off exoplanet.eu. And you can see that it's a nearly exponential increase. It was exponential until recently. And then we'll go back into that regime very soon. We at the moment have 4,800 planets in 3,500 systems. There are about 7,700 candidates still to be confirmed. And missions such as Gaia promised to yield another 10,000 planets, Plato mission another 3,000 planets. So this graph will go up and up. Most of these planets are transiting, so 75% are transiting. Then we have radial velocity measurements. If you measure the wobble of the star. Microlensing, which is of course very big at the IAP as well, is a smaller percentage, and imaging only has 12 so far, but it's quite promising. Yeah, so there's a huge discovery space at the moment, and we are a field that is just starting to really get into really big data at this point. So and that will drive machine learning techniques in the future. So if you look at the same diagram, but dispersed through mass and semi-major axis of the planet's orbit, you can actually see where the individual techniques are most sensitive. So the top, I don't know if you can see my mouse, but the top left, you get the transiting exoplanets detected by ground-based surveys. Then further down, you get the Kepler space mission, which is the most sensitive we had so far. Which goes into the Earth size and mass size regime, but quite far away quite often. Radial velocity, similar performance in the Neptune to super Earth regime. And on the other side, on the other extreme, we have directly imaged planets, very large planets, very far away, self-luminous. And I'll talk about them in a second. And then you've got microlensing somewhere in between. So ground-based surveys, so Jean-Philippe Viollet is the expert there, so do knock him, not me. And then obviously microlensing from space with Euclid, for example. So it's an interesting space because different techniques address different parts of the parameter space here, and they have different issues and problems, and hence there's a natural clustering to the field of exoplanets with their own conferences, as I said, and their own approaches. So it's not as homogeneous as a field as it may look from the outside. So if you zoom in a bit closer, it's just something I wanted to mention, because this is sort of the cutting edge of where we are with planet statistics at the moment. If you zoom in on the super Earth regime, so this is anywhere between say 1 and 5 Earth radii, we see that there's a natural clustering happening. So the super Earth gap, or the Fulton gap, because Fulton was the first to recognize that. And you can see that around 2 Earth radii, you get a depletion of planets found. So that might be the case that on the larger radius side, on the right-hand side of this diagram, you have primordial atmosphere. So you're more into the mini Neptune regime, planets that are just heavy enough to hang on to their original atmosphere. But planets that are smaller don't have that gravity to hold on and were stripped of the atmosphere, all have secondary atmospheres. So there are these stark phase transitions in planetary science that we're starting to see, which are very interesting and do require, a lot of data and a lot of data analysis. We can also say now, we can start making conclusions about planet occurrence rates, which is interesting. So we have the hot Jupiters, of course. These are the easiest to detect. These are, Jupiter-sized planets at several hundreds or thousands of degrees, with very, very close in orbit, of order of a day or two, sometimes. Cold Jupiters, like our own, less exciting, but are there. Super Earths, which are the most common planets in our galaxy, so anywhere between Earth size and Neptune size. And you can say already that, from these planet statistics, the probability of having a super Earth given a cold Jupiter in the system, so you detect the cold Jupiter first, because that might be easier, the probability of having a super Earth in the inner system is 90%. But vice versa, it's 30%. The other way around. And you can make similar conclusions with hot Jupiters and cold Jupiters. So this is all, still a bit vague, but we're starting to be able to reconstruct planet formation scenarios as general rule in our galaxy, rather than just looking at our own solar system and extrapolating from that. So that's been a lot of work since the early 2000s and the 90s really, and there's been a huge investment in space missions and ground-based telescopes and instruments. So this is just a timeline slide. It's still obviously up to date, but it's a bit older because it only goes to 2019 here. Of the exoplanet missions, or missions that are involved in taking exoplanet data. So Hubble and Spitzer, of course, are generalized missions. So is Gaia and James Webb, but they still provide loads of exoplanet data. And at the top, you can see that these are mission finding missions, and Cheops and Ariel are characterization missions, and I'll talk about that in a minute as well. So we are really at the golden age of getting a lot of data from these missions and also from ground-based instruments. So machine learning is an obvious way forward in this field, even though it's a young field, but people are really, I think, waking up to the idea. Now, what are the main challenges? Generally speaking, from a data perspective, well, they're not uncommon, and you will recognize pretty much all of them. Most of these have been addressed in the talks this week in different contexts. Exoplanet transit detection is a rare event anomaly detection in time series data. So that's relatively easy. Well, not easy, but well-known issue. Complex time evolution. So our time series are heteroscedastic quite often, and the sampling is quite often inhomogeneous. Component separation, so we have a convolution of the stellar noise, the stellar activity, instrument noise, and the planet signal. So component separation is an important part, PCA, ICA, MCA, so on and so forth. Severe class imbalance, you need to look at a lot of stars to find an exoplanet, and you need to look at a lot more to find a molecule in an atmosphere. So that's a very prevalent issue. Poor domain transference. Not every space mission is the same. So, what works on Kepler space mission doesn't work on TESS necessarily, because the underlying noise statistics are very different and poorly understood. And, inverse modeling of, very complex or unknown likelihood. So this is all pretty familiar to you, but, we're sharing the same issues as other fields. if you boil it down. So when I, started this talk, writing this talk, I thought like, okay, well, I'll do a quick search of where the main areas are that have embraced machine learning the most, and that it's unsurprising that these areas are the ones with data.
Ingo, I'm sorry to interrupt you, but there's like a
Yeah.
burst of static coming through in your microphone now. Is there anything you can do on your side?
Sorry, yes, it's probably my AirPods dying. Hang on, I'll take them out.
Okay. Yeah, it's like a static coming every 2 or 3 minutes.
Okay, is that better?
Yeah, that's fine. Yeah, go there.
Okay, yeah, sorry.
No problem.
My AirPods are on the last legs, and I thought it'll help, but it clearly didn't. Yeah, sorry about that. Yeah, so the field is can be subdivided in terms of machine learning into 3 major areas, and that's imaging, microlensing, transits, and theoretical modeling, so atmospheric transmission and atmospheric models. There are other fields that I'm not going to address necessarily in this hour, because it's just an hour, and it's there's only so much you can pack into a talk, and it's already full. But there's a lot of astrobiology, prediction stuff with machine learning, stability and body simulations, and so on and so forth. So yes, the field is very new, so that it really picked up on 2018, 2019 timescale. So again, we're lacking a bit behind cosmology, I think, in terms of timelines, but it's a very fast moving field, so we're catching up as fast as we can. So the battle plan for this talk is that I'll talk about machine learning in detection, so direct imaging, in transit detection and transit depth measurements. And then I'll move on to the more theoretical side, which is the modeling of atmospheres, inverse modeling, and if I still have some time, 2 slides on chemical network analysis. So there's apology to all the microlensers, the astrobiologists, the planet formation people, radial velocity people, and any other paper that I haven't mentioned. So with these review talks, you end up pissing off 80% of the field, because you've either neglected them or misrepresented them somehow, at least. So apologies that I've edited these out. So on the direct imaging side, this is a very interesting field, and it's very different to the rest of exoplanets, because you can actually see the planet directly. So this image here is a time series of HR 8799, the system, and the dots you see around there are the actual planets. So these are actual planets, and there's a time series of them orbiting. So that's quite astonishing. These planets are obviously self-luminous, so they're very young, so they're only a couple of million years old, and they're very far away from their host star. So this is usually just after planet formation. So you can see that the coronagraphic mask is 20 AU in itself in this example. Now, the contrast ratio, even if you use the best coronagraphs, well, the contrast ratio between planet and star is of the order of 10 to the 10, 10 to the 12 sometimes. And you need the best coronagraphic masks and stellar subtraction methods, to be able to actually get anything from the exoplanet. And even then you need, data analysis techniques to see them out below the noise level. So you need 8-meter telescopes. And at the moment, there have only been 12 planets detected so far. So this will hopefully pick up in the future, but it's a tricky system. Now, the issue with direct imaging is that you can see this on the right. This is real data after data analysis in 2015. You can see these splotches around the coronagraphic mask that look like a planet. So down here, B is the planet. Everything else also looks like a planet, and these are called speckle patterns. And this is the residual noise after the LEO stop. Differentiating between planet signal and residual stellar noise is very, very difficult, because they often share the same statistical characteristics. One trick to do that is because the stellar noise is instrument dependent, like the shape of that is instrument dependent, is quasi-static, and is pretty stable. So what people do is they switch off the derotator, the field derotator in their instrument, and just rotate the field throughout the night. So what basically happens is that the speckle patterns stay the same or very similar, but the planet moves around, as if field of view moves across. So basically the planet goes around the star here, and that's called ADI, differential imaging, angular differential imaging, and that's been used a lot to break this degeneracy between speckles and planet. Now, this said, just stacking those images together isn't working, so you need to do something more. And most of the times, people have used principal component analysis or SV support vector machines, or non-negative matrix factorizations, basically PCA-based techniques in the past to subtract the quasi-static speckle pattern. So there was a data challenge recently, so it was published this year, and you can see that the top two categories are basically PCA methods. The F1 scores here, so that's how well they've been doing overall, according to different metrics, and some inverse modeling, which is basically fitting the speckle pattern, and the first attempt of a neural network here. So you can see that the neural network is not doing too well so far, but I think this is one of the reasons here is that it's a supervised classifier of already PCA reduced data. So that means you're adding an extra uncertainty on the PCA uncertainty. So it's very difficult, I think, to get beyond PCA, the original signal to noise. So, but this is the first big attempt for the community to really look into different techniques and understand what is actually working and what is better or not. So it's a very promising paper. So there's interesting stuff out there. So beyond the PCA-based techniques, as good as they are obviously they're limited by the orthogonality of the components. For example, you're really dependent on the morphology of your signal. So if you have an edge on, a face on disk image, for example, the first principal component will take out all your signal and there's nothing left at the end. If you want to do an exoplanet detection, that's fine. If you want to do a disk detection, disk study, that's not fine. So there have been different techniques now which have been very interesting and very successful. So one is a morphological component analysis, and yes, and basically using PCA as components to a larger dictionary of possible features that you can fit onto the data to subtract speckle noise. So this is the PCA result, the original, and if you go to the MCA, you can see the difference. It's a much crisper image of a disk. It's not distorted anymore, and because morphological components can differentiate between different morphologies, so the disk morphology is in a diffuse, whilst the planet is it's basically just it looks like a hot pixel, basically. It's a delta Dirac function in your data. You can differentiate with them and use different dictionaries to find the planet. So here you can see that it's really nice, and the planet stands out as this hot dot here, or here and there, and these planet forming regions near the star, which can be retrieved. So this is really, really good work. The top is not normalized, and the bottom is a normalized image. So they're the same. So yes, people are really, this is a really new paper, only a few weeks old. Yeah, people are really investing in these techniques. Another technique is half-sibling regression. So looking at a noise as a causal model. So that's quite interesting, because here you model every pixel as a pure noise time series given other pixels around and the geometry of your observation, and any deviation from this noise model, which, you know, in the case there's a planet, there would be a bump in flux or, at a certain time of observation, because as you can remember, the planet moves around the star during your observation. Then you can basically identify this deviation, this outlier, to your noise model, and then predict where the planet should be given, you know, your field of view rotation in the next frame. And if it's still there at the predicted point, then, you know, you've got a planet. So it's quite a simple approach, but it works really, really well. Just assuming that instrument noise is independent of the stellar and planetary signal is a good way forward, and it's been done in a couple of different subfields in exoplanets. And you can see on the bottom left, the classical PCA approach gives you a signal to noise of 37 for this planet detection, which is still very good. But the final half-sibling regression causal model gives you a signal to noise of 160. So there's a stark improvement. Yeah, so it's a very interesting little paper. Now, the other thing with direct image planets and generally exoplanets is that we have no true negatives. You can't train for example, supervised techniques. So all these techniques are basically unsupervised or component separation so far, because it's very hard training anything supervised or semi-supervised, because we have no true negatives, because the negative label for a data set is always dependent on the state of the art of your detection technique. So that means there could still be a planet, but you just don't know there's a planet because you're not good enough to find the planet yet. So you don't have any true negatives, and you have only sometimes spurious positives. Sometimes the positives are very clear, but sometimes they're not. So we thought, you know, to solve part of this issue is to use generative networks and train them on real images of, in this case, a Hubble data. And by using a generative adversarial network on enough data and enough different angles, observation angles, you can assume that the likelihood the GAN learns is planet-free to a good approximation. And once the likelihood of that data is learned, you can generate new synthetic data, which is deemed more planet-free than the real data, and then inject planets for positive and negative labeled data set. So that worked very well, actually. So that we submitted in 2019 to the European Conference of Machine Learning. And, you know, it's starting to be used more in that field. But with planets, you never really have true negatives. So this is a prevalent issue. Now, for detecting planets, the transit method, as I said, is you know, the most prevalent. Is 75% where transits. And there are two subfields to transits. There's the pure detection, and then there's the characterization of the light curves. So here we've got some examples of typical Kepler planets and Kepler light curves. So Kepler is, you know, very, very good signals. No, it's probably still the best out of all the data sets. So it's, you know, if you start somewhere, start with Kepler. And you can see the different light curve morphologies here, depending on, you know, the star, limb darkening, and obviously inclination angle of the planet and size. Yeah, so the Kepler mission is unfortunately defunct now. So it ran from 2009 to 2013 and observed the Kepler fields up in Lyra up here continuously for that period of time. So we have one continuous time series pretty much, apart from a few small issues here and there. It was the largest camera at the time. And in 2013, two reaction wheels broke, so the spin axis couldn't be stabilized. So people used the solar wind to stabilize the mission, but at that point it couldn't focus on the Kepler field anymore, but did a general survey of what it could still point at. So that's the K2 mission, which was also quite successful. Then following the Kepler's demise, there's a fuel ran out in 2018. We had the TESS mission coming up, and the TESS mission is a very different approach. and it does an all-sky survey for exoplanets, and it scans a field at a time for 27.4 days, and continues to mosaic the local neighborhood. So the reason for that is that it's more likely to find brighter planets closer to us that are easier to characterize, whilst the Kepler planets are usually quite faint and too far away to do much with them. Yeah, so currently there are 4,500 potential planets, 161 have been confirmed so far. And after TESS, there will be later. So there's a constant stream of these planet detectors in the making. Now, most of the planet detections were done with simple Fourier analysis and box fitting. But in 2018, people started using neural networks for this. So the Schaum and Vandenberg paper was the first one, where they used the time series data in two convolutional networks that then fed into a fully connected net up here. And the idea was that we need to look at a global view, so a larger time series area, and then a local view of getting more detail on the transit, and then basically scan through the data. So that worked quite well. They found a few planets. That was then updated in 2020 by Hugh Osborne, and he did basically the same thing. So this is the same network, but he also added auxiliary parameters like stellar information and additional transit data, for example, limb darkening shapes and so on and so forth, probably. And that helped the net converge much faster. And you can see on the right hand side that this is on the left here is the global view, and then on the right is the sort of local view of the planet transit. Yeah, and by the way, the naming conventions in the field are a bit leave room for improvements for Astronet, Exonet, and there will be some other nets coming up, unfortunately. But yes, so more recently, there's a fun little paper. It's very short, and it's only 3 pages, basically with one message: screw you all, and basically pointing out that everything else prior to this has been way too complex, and the hyperparameter estimation hasn't been done properly, and you can do the same planet detection with 95% fewer parameters, right? So you drop the local view, which this paper says is prone to overfitting anyways, and drop most of the parameters, and you still get the very similar result out. So this is not new in other fields that people have come along and said, like, actually the original nets are too complex, and you can use sparser and pruned nets, and this is the same here. So that's called Genesis. Yeah, so that's an interesting paper. Now, once the planet is detected, the issue is about what do we do with that planet. We need to measure the transit depth to understand how big the planet is, and if we want to do spectroscopy of that planet, we need to know the transit depth of the order of 10 parts per million. So that's quite difficult if the instrument noise is sometimes 1,000 parts per million. So for example, here in the Spitzer case, so Spitzer was notoriously bad, so current data isn't quite as terrible, but these are the dark old ages, the pioneering ages, and I just like the slide to show people how difficult it was and still is in many cases to actually see the transit. So here the red is the noise model, and you can see the planet down there. So this is transit, and the bottom is secondary eclipse, and I usually ask the audience where the secondary eclipse is here, and you'd obviously say it's right there. It's absolutely obvious, and a high signal to noise detection. So very early on, sort of 10 years ago, people did these noise models, ad hoc, by assuming they know what the functional form of this noise model is, which led to quite a few controversies in the field, because depending on who reduced the data, you got a different transit depth. So machine learning was one of the first to then solve this, and this is kind of where machine learning really started in the field of exoplanets. And so the first sort of attempts are in 2012 with Gaussian processes, which you obviously all familiar with, where you model the time series as a multivariate normal distribution given a certain covariance. And the covariance matrix is, a bit of a matter of debate quite often. Most papers use the standard ones like square exponential and Matern, but there are also more custom-built covariances which, do yield similar results. It's been used very much since, especially in radial velocity in that field, which I'm not really going to talk about, but Gaussian processes is, still very prevalent there, and in time series modeling for stellar characterization mainly. So planets, there's still some planet papers, but the main beef is in stellar. Now, the other approach, which started in 2012, was instead of modeling the noise with Gaussian multivariate Gaussians, why don't we decompose the noise from the signal, assuming that the planet signal and the stellar signal are statistically independent from the instrument, which is always true. So we used independent component analysis back then, and that yielded quite a lot of papers. And the idea here is that if you go for photometry, so this is Spitzer photometry in the top, it's defocused. If you take an individual pixel as a time series, you can start detrending inter and intra-pixel variations, because the only common signal amongst them is the stellar signal. So that works really well, and that managed to resolve quite a few controversies in the field of people doing different data reductions on the data, getting different results. So in 2016, there was more and more of these techniques started coming up, and there was a data challenge organized by the Spitzer science team, and which we won quite nicely down here. So we were the most reliable and most repeatable algorithm. You don't get a prize, you don't get any money, but you get a single diagram that shows that it's all been worthwhile. And you can see that in most of these techniques, actually, within some error bar, actually converge relatively well. So that was Spitzer, and then there was a long time, not so much in terms of light curve detrending. There were similar ICA-based techniques and so on and so forth. Then Murray Morgan in 2020, and he'll give a talk later, so I'm not going to steal his thunder. I'm just going to advertise it. Improve the ICA using LSTM, so independent component analysis can be seen as a one-layer perceptron. But he basically used a multivariate LSTM. The idea we stole from Amazon, because that's how Amazon forecasts their pricing points. By taking everything into account under the planets, including weather and stock market, and that works really well. And you can see that this is the top here. This is blue is the raw data, and the red is the LSTM predicted noise model, and the bottom is the corrected data. And it brings the individual observations of this planet, which have been very discrepant, brings them more into in uniformity, so they agree much more by doing this analysis. So a lot of the debate on planet variability, if you observe a planet over several years and the signal changes, is not actually planet variability, but it's the variable noise and the changing noise characteristics over time. Not all methods work, though, and this is I wanted to highlight this paper because it's been a long time since I've read something quite as amusing, and it's well done for them for publishing it. And I said, this paper serves mainly as a cautionary tale and pathfinder for anyone else attempting this type of application of machine learning to systematic reduction. Because we had such promising initial results, we put a lot of effort into feature engineering and hyperparameter optimization in hopes of finding a better model. The lessons we learned are the following. And it's basically they used a random forest and used auxiliary data to try to reduce the systematic noise in Spitzer data, and it all looked very good by eye. But if you actually looked at the transit depths retrieved, their method performed worse out of all methods ever published. But the reason why I wanted to highlight this is not because it didn't work, but because publishing failures in model development is very important, right? It stops other people reinventing wheels that don't run. So it's very important, and it's a good paper for lessons learned on how these things can go wrong. It also points out that it's important to come up with consistent benchmarking data sets, similar to machine learning, where everyone has, celebrity faces. So on the characterization side, I forgot enough time. Yeah, on the characterization side, it's mainly about finding the planet's atmosphere. And why does the planet give us anything interesting in the atmosphere? Because by studying the atmosphere, we can understand what the formation mechanism is of these planets. We can understand what the impact history is of these planets, clouds, stellar radiation, escape processes, volcanoes, and of course, if you ask any media outlet, aliens. Right, so once we have the planets and once we can characterize the transit light curve correctly, then it's really the next step is to do this spectroscopically to get the spectra out of these atmospheres. Right, so I don't need to tell you how this is done. Some of the stellar light is filtered through the atmosphere on the transit. So this is of the order of 10, 20, up to, for large planet, 50 parts per million. And depending on the composition, you get a transmission spectrum out, which is obviously strongly attenuated by stellar activity, the stellar spectrum, so on and so forth. So it's quite a non-linear process that you need to model. Now, to speed up this modeling, because it takes a long time, we thought, at least a qualitative understanding would be even useful to start off selecting the types of molecules we need to put in. So in 2016, so this is the age before TensorFlow, so the dark ages of deep learning. We wrote a very simple MLP model called Robotic Exo-planet Retrieval or something, right? I mean, I'm as guilty as everyone else for shitty names. And that worked really well. Basically, it's a simple pattern recognition. It was bound to work, but it did work. So it was very good. Back in the day, machine learning was very, very new news, and the Daily Mail picked up on it. So if you don't know the Daily Mail, well, I guess since this is recorded, I'm going to just leave it as that. It's the Daily Mail. Yeah, but they came up with this headline: "Meet Robert, the alien hunting AI." So it's this AI looking for ET, and the way they illustrated Robert to the esteemed audience was with this picture. Yeah, which is just a humanoid looking at a bunch of folders. I don't understand why he would look at folders, given that he's digital. But that's basically what they got out of the paper, which is entertaining enough, I guess. So since then, things have moved on quite considerably, and people have been using very different techniques to solve this issue of this inverse modeling of getting from the spectrum to the planetary parameters, such as the abundance of water, methane, and temperature, structure of the planet. multiple techniques here. In 2018, we published an attempt with generative adversarial networks. So GANs, basically, because we don't know what the underlying likelihood is, so this is a likelihood-free method, so that might make sense. Works very well, but the issue with GANs is that you don't really know whether they've converged, and convergence is always an issue. If you ever worked with GANs, you know what I'm talking about. But it manages to generate very realistic spectra and get roughly, or actually most of the times, the exact right abundance ratios out. So that was very good. Different approach published at the same time was using random forests. Random forests are much better than GANs in terms of explainability. You can, literally trace the decision-making process. But the issue is here that they don't generalize very well. So this paper only works for one planet. So you need to almost retrain it for every planet. Then if you want to do data analysis on that planet with different multiple spectra, it's very fast and very good. But yeah, there's some training to be done. Yeah, you can see the predictions here. This is predicted versus real values. They're mainly okay. There's this bump down here veering off, but this is because there are basically no more features in the atmospheric spectrum. So any algorithm will struggle here. So this is quite good. People have then taken this on, and rather than using GANs, people have used multiple types of more straightforward MLPs and deep networks, convolutional nets, and so forth. A nice one here is PlanetNet. You see another of these names, where they've basically used an ensemble of Bayesian neural networks. The Bayesian net predicts a distribution of a parameter here by modeling the mean and the covariance, and by running multiple of these, you get an understanding of the uncertainty of the prediction. Now these are the sort of posterior in quotation marks plots, and you can see that it does hit the right spot in terms of maximum likelihood estimates, but there are no known correlations here. So there are clear correlations, for example, between temperature and water in exoplanets, and radius and water, for example. So these techniques don't necessarily pick up on all of that yet. So the current issues with atmospheric modeling are that the physical correlations are difficult to train. It's very much a maximum likelihood estimator at the moment. They don't formally account for the data error, so that means that the posteriors they produce are not formally Bayesian, and the generalization is not necessarily guaranteed. So these are pretty fundamental issues that we're working on. So another team decided to say, well, screw this all. We're going to just use neural networks to build faster surrogate models of atmospheric spectra, and use them in a standard normal nested sampling routine. And that gets past the correlation issue, and it gets past the posterior issue, and that actually works quite well. So surrogate models are, they've been seen in many other fields, and I think this is quite a good idea as well. So there's a recent paper as well. Now, as I said, there are multiple elephants in the room with this sort of work, and the obvious ones are, how do these networks really learn? What exactly do they learn? I mean, we're not giving them the physical model, we're giving them representations of the physical model, as in, we generate some data, or some simulated data, and then train this neural network on. We don't really understand how biased this approach is. What are the, in a sandpit scenario, yes, we understand what's happening, but if you apply this to real data, you don't have the advantage of knowing the ground truth. The uncertainties are difficult, so the Ensemble neural nets are doing a bit better in this respect, but still. There's this discussion about how complex these networks need to be. and how difficult it actually is. So the complexity in atmospheric models varies dramatically depending on your initial assumptions. For example, an isothermal atmosphere has only one free parameter, whilst a fully modeled atmosphere can have as many as thousands. So what physical constraints do we need to use? How do we approximate these? So there are quite a few things that are still outstanding. So on the what it actually learns and what the biases are, we thought we'll make a start. And Gordon Yip published a paper this year using explainable AI. So basically tracing back what the network thinks are important spectral features for the prediction of a molecule. And in this diagram here, you can see that actually it knows where to look. It makes sense to look at the places it does look to predict the abundance of a molecule. So that gives us hope that these neural networks actually do learn physics by example. And it's not only the molecular detections that make sense, but it also makes sense in the way it treats cloud cover. For example, clouds are more visible by reducing the Rayleigh scattering in the optical and the infrared. And it also needs a measure of how big and inflated the atmosphere is. So it looks at the lowest point and the highest point, similar with temperature and radius. So it gets complex secondary relationships out of this data, which is very, very good news. We also realized that we've trained, there's been a debate on what architecture to use, what's best. We've explored multiple architectures and realized that they're basically all relatively similar in performance. It's a matter of how you train them more than what they are. So that's another interesting aspect. Now, the other thing, so explainable stuff is going to be very, very important in understanding how we're going to progress in this field and what we can actually do with these neural networks and how, it must not be a black box anymore. And I think this is a way forward. Another way of breaking this black box behavior and informing the nets and improving convergence is obviously by including physics. And, there's been multiple talks on this. And in the AI physics hybrid models, which is also something that we're working on quite actively now. And the exoplanet transit model, for example, is an analytical model that you can include in PyTorch. So Myron Morgan again wrote a module for that, and then you can augment your normal transit modeling with a neural network that can take care of unforeseen systematic noise in the data, for example. So we think it's these two approaches. It's a bigger focus on explainability, and it's a bigger focus on physics risk-constrained modeling that will be important. The other thing is understanding complexity. There's an interesting paper by Fisher et al., and this is nearly my last slide. So yeah, I think there was some Slack comments maybe. Looking at the understanding complexity in very complex disequilibrium chemistry networks. So these are, packs of sometimes 100 or more ordinary differential equations that need to be evolved through time. But not every part of the network is necessarily as important to a planet type as others. So these authors here looked at where is the actual information contained in these complex networks, and how can we focus on that and map that. So they used they're the first ones to use graph theory to model this, and the next obvious step would be modeling chemistry with graphical neural networks that impose structure. And you can see here the complexity for a colder planet, 600 Kelvin, is much smaller than a hotter planet, as you have much more hot bands switching on. Similarly, evolving these chemical networks is very difficult because you have to evolve these ODEs over time, and this takes days or months to compute at times. There's an interesting paper by Grassi this year as well, where they used basically an autoencoder throughout to map your chemical network into a latent variable space, which is strongly compressed by a factor of 5, and then evolve the latent variable space through time in a very similar manner that you would evolve the ordinary differential equations in real time, and then map forth and back. So there are multiple training steps there. There's initial and final step, and then there's in between. But they can show that it actually works very well, and this compressed evolution actually yields very good techniques. So the wiggly lines as the real data in the normal space, and the dotted line here is the latent variable approximation. So you're missing a bit of structure, but not very much. So that's very good news. Just finally, quickly, we're running a data challenge at the European Conference for Machine Learning every year, not 2020 because COVID. And the idea is to focus on some of these issues and bring in the machine learning community more explicitly by packaging up some of these problems like chemistry and presenting it to the informed audience at machine learning conferences. So have a look at the website, it's still up. It's been I think it was the largest machine learning challenge in the last 3 years at that conference. So that's very good news. People are really interested in astronomy on the machine learning side. But find the domain knowledge required a very hindering factor. So data challenges are actually very useful to bridge this gap between those communities and bring people together. And finally, so conclusion, as you've seen, so it's a very fast whistle-stop tool, way too much content. ML is very rapidly increasing exoplanets. We still have quite a while to go, but we understand what the issues are, and we understand what the issues with ML related to exoplanets are, and are focusing on those now. There will be more and more data coming in, similar to cosmology, right? It's just going to be very, very big data, so we need these techniques. And the issues that we're facing are very similar to ideas in cosmology, very similar to ideas in other applied AI fields. So there needs to be more crosstalk, which is something that's happening now. So yeah, thanks very much.
Thank you, Ingo, for an excellent talk.
Since I can't see you, I have no idea whether you all just slept or not.
It was really great. We actually tried to get, Keelam sent a message to Randall Munro about using that cartoon on the conference poster, about the linear algebra. Do we have some questions in the audience? So I guess I'd make a comment. I don't know if you were able to participate in the debates or not, but what's the general feeling in the exoplanet community towards machine learning techniques? There's still a fair amount of skepticism, is there?
Depends who you speak to, right? Whenever I give a seminar, it's basically, not to be ageist, a certain generation is appalled and horrified by how black boxy these things are quite sometimes, whilst all the PhD students have already secretly tried on that GitHub account to make it work. I think there's a generational shift. It's a very traditional, it's a very young field, but it's also a very traditional field. Similar with planetary science, there are petabytes of really high quality data that have not really been explored with machine learning.
And so you feel it, yeah. So you feel then that the machine learning techniques will be essential for being able to analyze data from the future missions.
Yeah, absolutely. So, for example, the aerial space mission, just to give one example, we'll look at 1,000 exoplanets and characterize the atmospheres of 1,000 exoplanets in a mission lifetime of 3 years. So that means we need to have 3D atmospheric models almost instantaneously to know whether we need to go back to these planets or not. That will only be doable with machine learning, I think. Similar, the data exploitation in just transit detection or microlensing or direct imaging. There's a lot to be done. I think we're only really starting to understand how complex our data is, to be honest, I think.
And I like the comment you made about the paper where they talk about publishing their model failures. So maybe we can go back to that and you can tell us exactly what happened in their paper. You showed the start of the paper, but then you didn't explain afterwards what happened.
Yes. So I think what happened with that paper is the way they used the auxiliary information, such as or when you do spectrophotometry, the aircraft has quite a strong wobble, jitter. So you get very strong inter and intra-pixel variations because the Spitzer pixels are very non-homogeneous.
So it was overfitting.
Yeah, I think so. I think the way the random forest was set up, it was not the ideal way of getting taking that into account. But it's speculation. I would need to try that myself to actually fully understand what happened.
Yeah.
But it's the thing is that these data are so noisy sometimes that even though by eye it fits beautifully, but if you actually look at the mean of the transit, then you get a strong bias, and that bias can only be it's sometimes an order of magnitude below the systematic noise, so it's very difficult to understand where the issues come from sometimes.
And the techniques of now, I mean, one of question we've had quite a few times is assigning a correct statistical probability to a detection with machine learning systems. So for instance, in the transit detections, how do you do that now exactly?
You don't. It's a matter of ongoing debates, but at the moment all these techniques are completely overconfident. But with a transit detection, usually once you've got a candidate, it's relatively easy to follow up on that candidate. Quite often you need to do that. So with transits and Kepler, you need radial velocity measurements to disentangle whether it is a binary star system, a blended binary system, or something else. So there's always with us there's always like 3 or 4 other techniques that need to be done to be absolutely sure anyways. So in that sense, it's not been so important to get the exact probability right, because we just need an algorithm pointing a finger at here there's a potential transit.
So we've got a question on Slack. What's the state-of-the-art technique method in classifying light curves of eclipsing binaries? Very specific question.
In eclipsing binaries, I don't know. I would need to have a look at the.
Okay, no problem. You can interact with on Slack. Do we have some more questions from the audience? I think everyone is totally. Guilhem, you've got the microphone.
Yeah, actually, you showed like this nice thing, but like the critics that was designed to identify when you have a planetary system. It was like 1,000 images that maybe you augmented to 10,000. So, was there any risk of that the data set was too small there, or because it?
Yes. Oh, yeah. That was exactly the problem. So that's why we've kind of dropped working with Hubble, because there was only 1,000 good images and it's not enough. So what we managed to get the GAN to approximate the speckle likelihood to the order of factor of 2 of where we need to be, but not lower. So we need to go a factor of 2 better, and it was basically just the idea that the data wasn't good enough. So we're doing this now with ground-based XAO and GPy data, where you have terabytes and terabytes coming out every night almost, and that should be a lot more fruitful. But yes, you're absolutely right picking up on that. It was very limited.
Are there any more comments or questions? Everybody's really quiet this morning, but it was a long night. It was super interesting, and I guess we'll thank Ingo again. And if you have more questions, just ask him on the Slack.